start. Yeah, let me start the recording. Last Thursday, we started chapter 7, confidence interval estimate. So we didn't finish. Before we move on to section 7.2, we want to cover those two questions to reinforce what we have learned on last Thursday. All right. Yeah. So the first one is 19, number 19. Next question. The data given to the right includes data from 42 candies. 7 of them are red. So those are 7. The company that makes the candy claims that 34% of its candies are red. Use the sample data to construct a 95% confidence interval estimate of the percentage of red candies. What do you conclude about the claim of 34%? Yeah, let's see what's going on in this problem. So 42 candies, 7 of them are red. The company claims 34% of its candies are red. Use the sample data to construct a, oh, that's a lot of data. Okay. Construct a 95% confidence interval estimate of the population percentage of candies that are red. So this is about confidence interval estimate of the population proportion. Yes. First, we need to clarify that. That's the sample we have, right? I believe. Sample bag. So this is the sample we got. So we have 42. 42 would be the sample size. And 7 would be the number of success, right? Number of success, 7. Do you guys remember the function we apply to estimate population proportion using confidence interval estimate? Do you remember the function we use? Yeah. What is the name of the function in the calculator, TI-84 calculator? Exactly. Thank you, Kelly. One proportion z interval. Exactly. Okay, then let's go to our calculator. Turn on the calculator. And let's go to stat and go to the right twice and highlight tests. In the menu of the tests, we are going to select letter A, one proportion z interval. Yeah, let me write down the process. So we go to stat, and then we go to tests. Yeah, shift to the right twice. In the menu of tests, we're going to choose the letter A. The function, the name of the function in the menu we're going to apply is called a one proportion, PROP, z interval. Okay? Yeah, let's confirm that function. Yeah, what is the x? What should we enter for x? And now you would see the menu, the following entries: x, n, c, and then paste, calculate.
Can you explain where you got n and x to begin with?
Okay, that's a good question. As you can of the bunch of those numbers says a sample bag, weights of a sample bag of candy, right? Yeah. So we don't have to count how many values in the data set because it's given. It says the data given to the right includes the data from 42 candies. So that's our sample. Yeah, the sample bag has 42 candies. So the sample size is 42. As a number set, the number of values in the set is 42. So the sample size is 42. And what is X? Remember, X is the number of success or number of successes. So every time you get a candy, if the candy is red, then that's a success. If it's not red, it's not success. So how many red candies do we have? We have 1, 2, 3, 4, 5, 6, 7. 7. And it's also given from the question. It says 7 of them are red. That's how do I get N and X. Did I answer your question?
Yes, thank you.
Okay, no problem. So we have X and N, right? Yeah. So now, oops, what happened? Seven point one. We were on number 18 right here. Okay. Oh, good. So now you should see the menu, 1 proportion z interval, right? Yeah, int. So X, we should enter 7, right? For N, we should enter 42. And how do we enter the C level, confidence level? Is given by the question. It says, construct a 95% confidence interval estimate of the percentage of red candies. So C level, we are going to enter 0.95. All right, let's do that. Yeah, enter X, 7, enter the value of N, 42, enter C level, 0.95, and then calculate. Remember, you're gonna only enter one time. If you do twice, you probably, depends on your calculator, lose the result. Yeah, so only enter one time. And what I see right now on my calculator, I have an interval. The left endpoint is 0.0539 6, and the right endpoint is 0.27938. 27938. And I also have p hat. The sample proportion is 7 over 42. 1 over 6, of course, is around around 16 or 17%. So it's 0.1666 repeating actually, and n equals 42. Yeah, let me know. Do you have the same thing? Yeah, you are looking at. You should be looking at the same thing with the green that I just highlighted. And now we are going to look at rounding. Yeah, very, very important, the rounding instruction here. Type an integer or decimal, round it to 1 decimal place as needed. So the left endpoint, the lower limit of the interval, if we round it to, also very important. Do you notice that? Yeah, so the So it's a percent actually. They want you to enter the percent, not the decimal that is equivalent to the percent. They want you to enter the percent. So let's convert the two numbers as a percent. This one is 5.396%. And this right in the point, if we convert that to percent, we have 27.938%, right? Yeah, just move the decimal point 2 places to the right and then attach the percent sign. Yeah, what are we going to enter in the calculator? No, we're going to enter in the cell without the percent sign, so only this part. And round that to 1 decimal place. So it's going to be 5.4. 5.4 here. And right in the point, we're going to round it down because 3 is less than 5. So we round it down, we have 27.9%. 27.9%. Right? Yeah, let me see. Do you have the same thing? Yeah. Be very careful. What should you enter in the cell? Sometimes you know the answer, but you didn't follow the correct format, and they still mark it as wrong. I don't see numbers, but I see you say yes. So I would agree. I would assume you got the same thing. All right, you got the same thing. How do we interpret the result? Is the result consistent with the 34% rate that is reported by the candy maker? Yeah, they report or they claim 34% red candy. The red candy must be very special. 34%, but turns out 34%. Okay, look at the interval here. Does the interval includes 34%? Yeah, the interval is from 5.4% to around 28%, right? Yeah, it's actually the interval is to the left of what they claim. Yeah, they claim 34%. They overestimated the percent candies in a bag. Yeah. So no, we should answer no because the confidence interval does not include the 34%. Yeah, that's how do we actually test the claim that is given by the question. All right, any question about number 19? Yeah, we went over how do we use the technology TI-84 calculator. The function name is 1 proportion z interval to construct a confidence interval estimate for the population proportion under the given with the given confidence interval. All right. Any question about that? Yeah, be very careful. What are you going to enter in the cell? Yeah, not the decimals. That is equivalent to the percent. Instead, we're going to enter the percent point because the percent sign is already given. Awesome. Then last question, 21. Okay, number 21. As I said, one important type of this chapter, one important type of question in this chapter is to find the minimum sample size. Yeah, minimum sample size that we can that's sufficient enough, that's sufficient for us to apply the confidence interval estimation. Yeah. So the formula for this, let me write it again. The formula is n equals z alpha over 2 over z over e, to the power of 2, and multiplied by p hat and q hat. The end of Thursday, if you watch the video, the end of the Thursday, I derived this formula for you. Yeah. How did I derive this formula? I start from the margin of error formula, and then I solve the margin of error formula for n, and I derive this formula. You know, when we review, before we review for the coming tests, I'm going to ask you, I'm going to recruit not only the questions you want me to cover on the review, for the review, but also the formulas you want me to include in the formula sheet. Yeah. For the coming test, we want to provide you as a formula sheet, but you need to tell me what formulas you want me to include in the formula sheet. That's a very, very good opportunity for you to organize the content of this chapter. Actually, we're going to cover 2 chapters the coming tests. Yeah, for example, I would definitely recommend you mention this formula, right? Yeah, for the minimum sample size. All right, so that's the formula we need to apply for finding the minimum sample size when we do the confidence interval estimate. Let's read the question number 21. The brand manager for a brand of toothpaste must plan a campaign designed to increase brand recognition. He wants to first determine the percentage of adults. How many adults must be serving in order to be 95% confident that his estimate is within 6% of the true population percentage? Yeah, it's a very practical and reasonable question. Before you do your survey, the first thing you need to determine how many people you are going to survey, how many subjects you are going to ask question, right? Yeah, so that is sample size n. And in this case, the 6% is a margin of error. It also makes sense you determine your margin of error ahead of time. Yeah, you control your risk. How accurate you want your estimate to be, you control that. So here E is given, predetermined. E in this case, margin of error in this case is 6% or 0.06. All right, margin of error is given. Okay, so part A, assume that nothing is known about the percentage of adults who have heard of a brand. This is also very reasonable, right? The assumption, because we are trying to estimate the population proportion. We want to estimate how many percent of the adults who have heard of the brand. Of course, we don't know. We know nothing about it. So that is a very reasonable assumption. Yeah. I have a question. What does the p hat mean in the formula? What does the p hat mean in the formula? By the way, p without the hat is the population proportion. What is p hat in the formula referred to? If p is the population proportion, what is p hat? Sample, no, I'm sorry, it's x. Normally x is the number of successes. We do not know the number of successes in this case. We don't even have a sample yet. Before you even started survey. P hat, oh, the value, okay, Dustin, you go too forward. You go too far ahead. My question, the answer I expect you to give me is sample proportion. Yeah, P hat here is the sample proportion. But guys, we don't even have a sample yet. Yeah, we don't even have a sample yet. How do we know the sample proportion? You know what I'm saying? So we do not know P hat. So P hat here, if P hat is unknown, that means the Q hat is also unknown, right? Q hat is 1 minus P hat. So part A is a very reasonable, practical assumption. Before we even go ahead to collect the sample, and our purpose here, goal here is to determine the sample size. Of course, we do not know the sample proportion, right? P hat is unknown. Okay, very good. So this is what we do. Now, how are we going to apply the formula to find the sample size n? By using the formula. Yeah, E is given. E is 0.06, predetermined, right? Yeah, that is given. In the case that P hat, Q hat unknown, Dustin already said, yeah, if we don't know, then we want to use half to be the value of P hat. Same with Q hat, because the P hat and the Q hat have to add up to 1, right? Yeah, so in a case that p hat, q hat are unknown, we use 50%, 0.5, yeah, as a fraction, half, to be the values of p hat and q hat. Because this way is more reasonable by using other numbers. Okay, yeah, this is more reasonable than using other numbers. Use 50%, half chance success, half chance failure. Yeah, is more reasonable than other numbers. If you want to know why do we use half, why do we use 50%, then if you were the mathematician, you were the statistician, what number you want to use? Use 60%. Why 60% is more reasonable than 50%? 50% is more reasonable. Okay, here we use 50%. Okay, you ready to find the z sub alpha over 2? The critical value here depends on alpha. Okay, yeah, I think we have done at least twice of getting the value for critical value. Here we're going to do it again. Yeah, as long as we know the confidence level, yeah, confidence level is predetermined as well. Yeah, confidence level determine how reliable you want, right? Yeah, margin of error determine how accurate you want your estimate to be. So here, 1 minus alpha equals 95%. Start from there. And then find the alpha. Alpha would be 5%. And then find the half of alpha. Half of alpha is 2.5%. Right? And which is 0.025. And then we're going to draw a z-curve. Z-curve. Not the best, but you know. So this value is going to be the z alpha over 2. And the area of this region is going to be alpha over 2. Yeah, 0.025 or 2.5%. Yeah. But what we really use is the area of the yellow region. Okay? Yeah, the yellow region and the red region together make 100%. So tell me what's the area of the yellow region? 1 minus alpha over 2, right? Yeah, if that is alpha over 2 in the red region. If the red region has area alpha over 2, then the yellow region would have area 1 minus alpha over 2. In this case, it's gonna be 0.975. Okay, yeah, sometimes I don't even do the math. Yeah, sometimes I don't even do the math. I'll just do 1 minus 0.025. Calculator ready? So we are going to go to second vars and then select the function inverse normal. Okay, guys, yeah, let's go there. Turn on the calculator. We go to second vars. Yeah, in the distribution menu, we are going to select inverse normal. And now you're gonna see a menu, a bunch of things that you need to enter values for. Area, mu, sigma, paste. Okay, the area, yeah, you don't have to worry about what is 1 minus 0.025. Most of the time I don't even do that math. I'll just enter 1 minus 0.025. The calculator would do the job and correctly, right? And mu is 0, sigma is 1, and paste. I got 1.95963. Yeah. So I would round it to 1.96. Yeah, 1.96 actually is a very common used critical value. Reason is because 95% is the most common used, mostly common used confidence level. So when the confidence level is 95%, you know I actually know this value because we use 95% as the confidence level so many times. Yeah, eventually you will have a very strong impression about this value, critical value. Yeah, that's the critical value corresponding to confidence level of 95%. All right, so that's 1.96 critical value. So now we are ready to enter everything in a calculator. Use the formula to find the n. Would you like to do that with me on your calculator? So z here is 1.96. 1.96. What I would do is this, okay? I would do 1.96 divided by 0.06. I have 32.6666 repeating. That's what I have, the quotient. And then I'm going to raise that to power 2. This is how do you raise to power 2. Find this key, shift key, 2. Okay, raise that to the power 2. Okay, that is right below the clear button. Raise to the power of 2. Yeah, you will see answer to the power of 2, and then enter. And now I have 1067.11, 1 repeating. And then what do we do? I'm going to multiply by 0.25. Yeah, half times half is 1/4 or 0.25, right? Multiply by 0.25. And let me know what you have. Yeah, the decimal I have is 266.777778. Yeah, we're gonna round it up. The reason, perfect, yeah. The reason we round it up is not because it is 266.7. 7 is bigger than 5. It is we always have to round it up. Even the decimal we got is 266.001. You see what I'm talking about? Always round it up. Yeah. Otherwise, you will have one subject short to guarantee your confidence level interval process. Okay. Yeah. Very important thing that we want to pay attention when you take the is the thing in the parentheses. The computer is very slow. So this here, round up to, okay? Oh, not this one. Part 8, where's you on part 8? Ugh, my system, my OneNote crashed. Let me restart it very quick. My point is, when we need to find a minimum sample size, we always have to round it up, unless the answer is a whole number. But that is very rare, I'm gonna tell you, especially when you use a half-half. 7.1, okay. Question 21. So I was going to emphasize this, round up to. Normally you do not see the word UP. Then you just follow the normal rounding rule. When the system specifically tell you round up to, you have to really round up to means even your answer is 266. Let's say 12, right? Yeah, even normally you should round it down, but no, in this case you're gonna round it up. Even this digit is less than 5, because otherwise you would have a shortage in the sample size that could satisfy the sample that you get will shortly will have something will not satisfy the condition you want. Yeah, the confidence level and accuracy. Is that guys? This is a good question. The first part, when P hat, Q hat is unknown, we use 1/2 or 50% to substitute for their values. And part B is another case. Part B is another case. Part B says, assume, yeah, based on the historical data, yeah, in the past, yeah, assume a recent survey, very recent, of course, the latest the better, right? Yeah, a recent survey suggests about 80% adults have heard about the brand. Yeah, sometimes you do the research, many other people do the research as well. Then you can probably like borrow their data, right? The result. So here, P hat is given. P hat in this case, part B is 80%, or 0.8. Then Q hat would be 0.2, right? Then when you enter the values into this formula to find the value of n, then you're gonna use, this is gonna be 0.8, it's gonna be 0.2, multiply together, you have 0.16, right? And you're gonna multiply 0.16. Yeah, so let's do it again. Let's do it again. So we're gonna have 1.96, that's the critical value, divided by margin of error 0.06, and we got a quotient, and then raise the quotient to the power of 2. Yeah, again we see 1067.11111, right? And then we're gonna multiply that by 0.16. I got 170.737777 repeating. And we round it up, we have 171. Okay? Yeah, make sure you have the same value with me. The college does give us a laptop, but it's not screen touch. It's not screen touch, so how do I write without screen touch? So I'm still using my old laptop here. Not the ideal device. Okay, very good, perfect. All right, you must have something like that for the test for sure. Yeah, even it's not proportion, it might be sample mean. Yeah, either this or that. The process would be the similar. Yeah, we want to know we want to pay attention with two things. First thing, in the case that P hat, Q hat are unknown, we want to use 0.5 to substitute their values. Okay, that's the first thing. Second thing, once you have the value of n from the calculator, you want to always round it up. Always round it up. Okay, even the tenth, like the digit right after the decimal point is less than 5, you still want to round it up to make sure your sample size is sufficient enough to apply the process. Okay, the two things are very important. And if you have a formula, then I don't think it's difficult to do this type of problem. Yeah, remember to include this formula when I recruit the formulas for the formula sheet of the exam when you receive the email. Okay. All right. Any questions, guys?
Hey, Professor, I just messaged it, but I know it's hard to say. But the textbook's formula is slightly different than yours, even though it might be the same.
Really?
But theirs shows as z alpha over 2 square root times p times q all divided by squared. So the entire denominator has both p hat and q hat over it.
Okay, I got you. You are talking about this formula.
Yeah, so I'm just I mean, I'm looking at
I think
the
you are talking about
chapter 7 sample size determinant proportions and means, and it just has E squared underneath the entire thing.
E squared the entire. Second, it's very slow the computer.
Yeah, you're.
Are you talking about? No.
I'm looking at the formulas and tables for the textbook.
Yeah. I'm
And
sorry,
it's
you cut
chapter
off.
7
Are
sample
you
size
talking about that?
determinant.
Oh. It's different from mine.
For if you're determining
My
n,
formula is correct. Maybe.
So look at the textbook's formula for n equals, so not from E, but from n equals. It just looks different to me than yours.
Okay. So did you try that formula? I believe both of them are correct. It's just the way it looks different. I think mine is very convenient. All you need to do is critical value divided by margin of error, and then raise to the power 2, and then multiply p hat and q hat. P hat and q hat is supposed to be in the numerator, by the way, not possible in the denominator. That I'm very sure.
Yeah, it is in the numerator in the textbook.
In your formula, you mentioned. Yeah, then it's supposed to be in the numerator. I would say the same, probably the same, just looks different.
Okay.
All right.
Thank you.
Yeah. I would. Yeah, no problem. Yeah, should be the same. Okay, so are we good to move on to section 7.2? 7.1 is about constructing a confidence interval estimate for population proportion. 7.2 is to do the same thing, but for population mean. Yeah, different parameter. Yeah, let's see. Okay, so we are ready to move on. Awesome. 7.2, we have a lot to cover. All right. So in this section, we're gonna also do 3 things. All right. First thing, point estimate for the population mean. Yeah. Firstly, let's recall what's the notation for population mean. Mu. All right. Mu is the notation to represent the population mean, and the corresponding statistic, sample statistic, sample mean. The notation for sample mean is x bar. Okay, notation for sample mean is x bar. Yeah. So the first thing is how do we do the point estimate? Point estimate. Only one thing we need to know about this part. What thing? Sample mean x bar is the best point estimate of population mean mu. If we are about to estimate value of mu by using one value, then you would have to consider sample mean. What else you think could do better than sample mean? Of course, the sample mean, right? And that's it. That's about it. No more things that we need to cover. Second thing is how do we construct a confidence interval to estimate population mean? The process is very similar with the previous section. Yeah, when we construct a confidence interval estimate for population proportion. But of course, this is going to be different. Yeah, but the process is similar. The confidence interval for the population mean is an interval centered at x bar. Okay, centered at x bar. With radius e. E is the margin of error. Okay, it represents or describes the accuracy of your estimate. Yeah. So here we're gonna have x bar plus e, and here we're gonna have x bar minus e. Yeah. So the confidence interval for population mean is centered at sample mean. Sample mean still play a very important role in this type of estimate, confidence interval estimate. I think that's very reasonable to understand, very easy to understand, because the sample mean is from a sample, is the statistic corresponding to the population mean. Of course, we have to use the sample mean. It doesn't matter what method we apply. All right, so number 3 is we are going to find the minimum sample size to guarantee that we could construct a confidence interval with the predetermined confidence level and a predetermined margin of error. So that's the third thing. Let's see, how do we construct a confidence interval for sample mean? For population mean, yeah. How do we construct a confidence interval for population mean mu? This is how. Formula-wise. Yeah, x bar is the center, no problem. Once you get a sample, you add up the values in the sample, divided by the sample size, you have the x bar, sample mean. Margin of error E, yeah, that's what we need to talk about in detail. Margin of error E is given or could be found by using this formula. T sub alpha over 2 times S over root n. I'm going to spend a little bit of time to cover why the formula look like that, all right? But again, the explanation or the proof of the formula is not the focus of this course, it's beyond the scope. But I want to try to explain as much as I can, okay? Yeah, here, I'm going to mark that in green. Based on the central limit theorem, we know that sample mean is normally distributed, right? Yeah, remember central limit theorem? Either the population is normally distributed or the sample size is bigger than 30, right? Then x bar is also roughly normally distributed with mean mu and a sample with mean mu and standard deviation sigma over root n. You remember that, right? Yeah. So if x bar is normally distributed, and if we could standardize x bar like this, yeah, subtract mu from x bar and then divide the difference by the standard deviation, we would have a z distribution. Z distribution is the standard normal. All right, yeah, because x bar is normal. Once we standardize x bar, we got a standard normal distribution. All right, yeah. However, we cannot use this standard normal distribution to find a formula for the margin of error E. Is because we cannot use this formula. We cannot use this because sigma is unknown. Let me explain why. Yeah, let's recall. Our goal here is to estimate population mean mu. If we don't know the population mean mu, very likely, or probably we do not know the population standard deviation either. Because the standard deviation has to use mu in the formula. You know what I'm saying? So that is a very reasonable assumption. So in this section, we assume sigma is unknown. All right? Yeah, because we are guessing, we are estimating the value for mu, and you know the sigma already. How is that possible? So more reasonable assumption is sigma, the population standard deviation is unknown. That's the reason we cannot use this distribution. We can't, because the sigma is unknown. You know what I'm saying? Then we have to figure out a way. Then what should we do? We are going to replace the sigma. We are going to replace the sigma with what? with S. What is S? Sigma is the population standard deviation. S is the sample standard deviation. Since the population standard deviation sigma is unknown, then if you were the statistician, you probably would agree that's a good idea to use the sample standard deviation to replace or substitute for the population standard deviation, right? Yeah. However, after you replace sigma with S, and the variable is not a standard normal anymore. It's a brand new distribution. Okay? Yeah. Once you replace the sigma with S, we do not have the standard normal anymore. We have a brand new distribution. Is called a T distribution. T as in Tom or tomato, T distribution. T distribution is discovered by this guy. What's his name? What's his name here? Gossett. I remember it's called a Gossett. Oh, I don't have this here. I remember his name is Gossett, and he wasn't even a statistician, or he wasn't even in the academic field. He worked for a brewery, but for the work reason, he needs to find a distribution that could accommodate small sample size. So he discovered, I would not say invented, because the distribution is there. He discovered the T distribution because the company he worked for prohibit employee from publishing any paper use the real name. He has to use his come up with different name, like a fake name or something. Yeah, so he called himself, he published the paper with a student. Very humble, right? Very humble. We should pay greater respect to this. I would call him a mathematician for the result, for the accomplishment he has achieved. So we name this distribution after his name, student, but actually his real name is not student. Well, he could name himself a superhero distribution, but he chooses student means he's a very humble person. Yeah, it's very good. So this is a T distribution, okay? Yeah, if we have a sample mean, and then we standardize it, and then we switch the population standard deviation as a sample standard deviation, we would have the T distribution. T distribution. In fact, yeah, as you can see, we switch the sigma to S. We go from standard normal to T distribution. In fact, there's a closely related relationship between standard deviation and T distribution. When n approaches infinity, T distribution approaches to standard normal. So the curve, T curve, the density curve of T distribution looks just like standard normal distribution curve, like a Z curve, Yeah, a little bit different, but very close. Yeah, the only difference is standard normal use sigma, T distribution use S, sample standard deviation. Okay, and when you need to do the homework, you actually need to know those information. Even the proof of the information is beyond the scope, but I think it's good you write it down. Yeah. So the T distribution has a center, has a mean 0, and the variance is n over n minus 2. not a standard deviation. Okay, it's a variance. T distribution. Yeah, that's T distribution. We know normal distribution, standard normal has mean 0, standard deviation 1, right? Yeah, but T distribution is different. The mean is still 0, still centered at 0, but the variance is more complicated. Is n over n minus 2. Yeah, you might wonder, how do you get this formula n over n minus 2? I can prove, but it's very time consuming. Yeah, basically the variance is this, and for e of t, you have to use the integral. You have to multiply t by ft, the density curve, and you have to do the integral. And similar with that, t squared, and you plug in and you get that value. But again, we do not care about how do we get a formula. We only need to know that's the formula. And you don't even have to know the formula. All you need to know is v of t is bigger than 1, period. Okay, it's not 1, it's bigger than 1. Then we can do the homework. All right? Any questions so far about the T distribution, the student distribution, famous student distribution? Let's summarize. T distribution, what kind of variable is T distributed? This variable is T distributed, all right? And the T distribution has a is centered at 0, so the mean is 0. The variance is bigger than 1, not equal to 1. When the n sample size approaches infinity, T distribution approaches Z distribution, or the standard normal distribution. And another thing we want to explain is this n minus 1 is the degree of freedom. Yeah, degree of freedom is the only important parameter of T distribution. And so that's why we put them in the parentheses. T of n minus 1 means this is a T distribution with the freedom of degree, with degree of freedom n minus 1. Why is n minus 1? It is because if we have n values, x1, x2, xn, and x bar is given, right? Yeah, once we have a sample, we know the sample mean. Yeah, so means that if we add them all together, divide by n, we have x bar. So that is one condition. When you have n values or n variables and with satisfy one condition, then you would have you actually have n minus 1 variables, like a freedom. We have a paragraph to explain the degree of freedom. Finding a critical value requires a value for the degree of freedom. In general, the number of degrees of freedom for a collection of sample data is the number of sample value that can vary after certain restrictions have been imposed on all data values. For example, if we have 10 values and we know their sum, well, their mean is 80, that means their sum is 800. If their sum is 800, then we can freely assign the first 9 scores. Then the 10th score would be derived by using the formula, by using the restriction. They add up to 800, right? So we actually have a 9 as degree of freedom, not a 10. Yeah. The 10th score would then be determined. So in this case, there are 9 degrees of freedom. For the methods of this section, the number of degree of freedom is the sample size minus 1. Yeah. Or let's just remember, T distribution has a degree of freedom n minus 1. Yeah, that's about student distribution. Any question about it? Yeah, why do we need to learn the T distribution? Because that's how do we, yeah.
So just to reiterate, degrees of freedom is just n-1, and that's sort of what I guess we need to know and understand.
Yeah, exactly. Exactly. In order to learn a distribution, it takes a lot of effort. We really just, this is elementary statistic. We don't even learn. You guys probably haven't not taken calculus yet, so really hard to go deeper. For us, just know a very important thing about the t distribution is the degree of freedom. And t distribution has degree of freedom n-1. N is the sample size. So degree of freedom is the sample size minus 1. That's all we need to know. Okay? Yeah, so why do we need to explain that? Because in order to find the margin of error, we need to know t, the critical t value. That's the reason. Yeah, don't worry about that. Critical t value, the process we find critical t value is very similar with the previous section when we need to find the critical z value. I'll show you later, okay? I'll show you later. But you know what? Some of the questions we don't even need those formulas. We use technology, okay? Yeah, let me find a question. Let's start to get into the examples. Yeah. In theory, those things takes a long time to explain. Let's see which question I was about to talk about. Okay, we're going to do number 10. Okay? We're going to do number 10. Let's read the question. A food safety guideline is that the mercury in fish should be below 1 part per million. Listed below are the amounts of mercury found in tuna sushi sampled at different stores in a major city. Construct a 99%. Okay, let me write it down. 1 minus alpha is 99%. Construct a 99% confidence interval estimate of the mean amount of mercury in a population. Does it appear that there is too much mercury in the tuna sushi? All right. So calculator ready. Okay. So we're going to go to stat. Oops. STAT. Go to stat. And then shift to the right and highlight tests. And you would see a menu, a list of functions, right? Yeah. And which one we are going to use? Yeah, this is still interval, right? Yeah, estimation. So the one we are going to use is number 8. On my calculator is number 8. The name of the function is t-interval. T-interval. All right, yeah. So you are going to click or confirm that function, and then you would see this. Yeah, you would see input, IMPT, and you would see two options for the input. One is data, the other is stats. Yeah, let me write it down first, and now I'll tell you what to do, okay? So I have this x bar, I have s sub x, sample standard deviation, and we have n, we have c level, we have calculate. Okay, so let me ask you, let me ask you, do we have a sample mean given in this question? We are given a raw data, we are given a sample, but are we given the sample mean, sample standard deviation directly, that the values there that we can apply? Do we have that? No, yeah. No, we don't. What is that? Caps lock. We don't have the stats, okay? So we have data. Yeah, we have data, exactly. So in this case, you are going to confirm data, right? How do you confirm? You're going to shift the thing on top of data, make sure it's blinking, and you have to enter. It's not just blinking, you have to enter to confirm. Yet once you have data confirmed, okay, once you have data confirmed, so earlier it was here, right? Once you have data confirmed, the menu would look different. The menu would look different. You would have a list. List. Yeah, we don't have list. Yeah, list and the frequency and the sea level and the calculate, right? Yeah. So you know we decide to use this one because we do not have the stats given directly, right? All right. That means we're gonna second mode get out first. Yeah, let's get out first. Get out first, and then we go to stat and add it. And then we are going to enter the data, the values in L1. Yeah, go to stat, add it. Yeah, I'm going to clear my L1 and I'm going to enter those values in L1. Yeah, 1, 2, 3, 4, 5, 6, 7. Not too bad. So the first value, 0.57, enter. Second value, 0.75, enter. Third value, 0.1, and then 0.91, and then 1.27, 0.52, sorry, 0.51, 0.82. Okay, yeah, that's the most tedious part every time. Yeah, but you know, we have to do this, right? Otherwise, what do we do? That's the only technology available when you take the test. Okay, let me double check very quickly. All look good. Okay, so now we can go back. Yeah, now you're gonna enter stat and shift it to the right twice. And in the menu, in the list of tests, we are going to select T interval. T interval. Oops. I entered the wrong one. Okay, T interval. Number 8. You remember T distribution, right? Okay, so on the list, I'm going to enter list 1 because I have my values stored in L1. All right, L1. And let me know if you need help with enter L1. How do you enter L1? It's second one. Yeah, you enter the blue key, purple key, the blue purple key second, and you enter 1 is on top of 1 is L1. Yeah, and then I can just leave the frequency as 1 or just nothing. Yeah, go. Oh, so if nothing, they don't let my calculator doesn't let me proceed. So I just leave the number 1 there. And then go down. Confidence level 0.99. 0.99. And then it's 0.99. And then go down, calculate. All right. So let me show you what I have. Now on my calculator, I have an interval 0.19301, comma 1.2156, close the interval, and I have X bar 0.7. We don't really need those, but it's given as extra. 57143, and x s sub x is 0.36 486 788 22, and then n equals 7. Okay, I want to make sure that you have exactly the same thing with me. Do you? Yeah, awesome. Thank you, Miranda, Dustin, Kayla. Yeah, you guys have the same thing with me. That's awesome. Very good. Let's see what's the rounding. It says round to 3 decimal places, right? Yeah. So I'm gonna enter 0.193 here, as you can see. Enter 1.216 round up. Yeah, right here. So that's the interval. That's the interval. That means the mercury, the chemical, not chemical, as the metal actually, a certain metal I would. Mercury is a metal, right? Yeah. In the tuna, sushi, the mean is between 0.193 ppm to 1.216 ppm. And does it appear that too much mercury in the tuna sushi? Do we have a standard? Do we have a criteria here? Criteria says the safety guideline says should be below 1 part per million. Below 1. Wow, that's not below 1. The whole interval is bigger than. Oh, hold on. My bad. The 1 is in the 1 is in the interval. 1 is in the interval. So this is a 0.193 and this is a 1.216. Below 1. Well, still not completely less than 1, right? You see, because there's part of the interval is bigger than 1. So we would say too much because it is possible that the mean is greater than 1. Also, at least one of the sample values exceeds 1. So at least some of the fish have too much mercury. Yeah. So if we have an interval, the maximum or the right endpoint of the interval is less than 1, then we can safely say those tuna fish is safe, right? Yeah, but this is not completely, you cannot guarantee is safe because the right endpoint, the interval passing 1, a big portion passing 1. All right, so the main purpose of this question is to show you how do we use technology to construct the confidence interval for the population mean. And this question did not give us the stats. Instead, it gives us data. So that's how do we handle it. In the case it gives us stats, then you just need to enter x bar as the sample mean here, sample standard deviation here, and n here, sea level here. And then you will have the interval from the calculator. All right, I believe you can do that. Since we only have 11 minutes left, we are go ahead to cover the last thing of section. Yeah, how do we find the sample size that's sufficient to estimate the population mean with a certain predetermined confidence level and a margin of error. Yeah. So the formula you are going to use is this formula. Okay, is this formula. I want to ask a question to see if you can answer me. In section 7.1, the margin of error, yeah, when we estimate the population proportion, the formula for margin of error is this, right? And the formula to find the minimum sample size is a derivation, is derived from this formula. Basically, the two formulas are the same formula. So we have n equals z alpha over 2 over e square p hat q hat. So basically, those two formulas are the same formula. But for when we estimate a population mean, this is the formula for the margin of error. Why don't we modify, or solve this formula for n and use that formula to find the minimum sample size? Why this formula looks so different? Look here. Look at this one, this one. Why they look so different? This formula doesn't even have t alpha over 2. It's a z alpha over 2. And this is S, but this is sigma. It's completely two different formulas. Anybody can answer that question? I know the answer, by the way. Yeah, anyone could make sense why? Yeah, why don't we just use that formula? By the way, we are trying to start our research. Yeah, we have a predetermined confidence level, the reliability, and a predetermined accuracy, the margin of error. Yeah, but why don't we just plug in here and the n? And we need to plug in here to find n. You need a large sample size. The reason actually is because we do not have S. It's kind of interesting, right? Because you are going to determine the sample size, means you do not have a sample. If you do not have a sample yet, how do you know the value of S? That's why we can't use this formula. All right? Then you would ask, does that make sense? Because we are trying to find the value for n. So that means we don't have a sample yet. We don't know the sample size, so mean we don't have a sample yet. If we don't have a sample yet, how do we know the sample standard deviation? So we cannot use this formula. But then you're gonna wonder, if we don't know the sample standard deviation, then we're gonna know the population standard deviation? Yes. We would have to, if we don't have a sample standard deviation, we would have to, based on the historical data or related similar research, to find a substitution for sigma. It is better because it's closer to sigma. The reason we settled with t earlier is because we do not have sigma available. S is just a substitution for sigma. If we could, if we do not have S, we also do not have sigma. Of course, we want to find a closer historical value for sigma, not for S. You see what I'm talking about? Because we want sigma, not S. So here, sigma is gonna be the population standard deviation in the value from the past, some other research result. That's the reason this formula is completely different. And I think that would be enough for us, just to know the formula is different. Okay. Okay, that does make sense. Okay, thank you, Kelly. A lot of details, if I don't cover, would be very like dry, and yeah, why do we even do this? Why suddenly, a different formula? But if I explain, I have to control the level, because if we go too deeper, that's too much. We don't really need that. So just touch the surface, have a sense of the something behind it. Okay, so we're gonna look at question number 14. All right, we're gonna look at question number 14 for that. Yeah, let me see what's the formula. Square. Okay, got it. Number 14. Number 14. Number 14. I prepare many, but we don't really have time to cover all of them. 15. 14. Okay, here's 14. An IQ test is designed so that the mean is 100 and standard deviation is 19 for the population. Oh, here, let's see, you see that? For the population. So we have a mean here, 100. Here, 19. For a normal distribution. For a normal distribution. Okay. Find the sample size necessary to estimate the mean IQ score of a statistics student. The population is different, right? I think this population is for all the people, and this the population mean we are trying to estimate. That population is all the statistics students, yeah, such that it can be said with 99. So 1 minus alpha is 99%. Confidence that the sample mean is within 5 IQ points. Okay, so that means E, margin of error, is 5. Okay, so predetermine the reliability. The confidence level is 99%, pretty reliable, very high. And the margin of error, the accuracy is 5. Yeah, no more than 5. The error is no more than 5. The mistake. Assume that sigma is 19. Yeah, so you see, we don't know the population standard deviation of this population, right? Statistics students population. But this sigma is from the whole population, all the people, not just the statistics class students, maybe English students, business students, and so on, right? Yeah, but this is a suggested, recommended sigma value, and it determine the required sample size using technology. Then determine if it is a reasonable sample size for a real world calculation. I use the formula n equals z alpha over 2 times sigma over e and then to the power 2. Let's see what we need to enter in this formula. I do not remember we have a technology for that. You would have to enter the value. Use a calculator. Okay, calculator is that. Okay, so firstly, we have to take care of this. Okay, take care of z alpha over 2. Let's do it together here. Start from 1 minus alpha. %. Then alpha would be 1%. Alpha over 2 would be 0.5%. 1 minus alpha over 2 would be 99.5%, right? Yeah, so we are looking for the critical z value. This area, this region, area is alpha over 2. This orange region has area 1 minus alpha over 2. Yeah, 1 minus alpha over 2 is 99.5%. Yeah, or simply just 1 minus 0.5%, right? Yeah, so if alpha over 2 is 0.005, then the orange region would be 1 minus 0.005. 0.5%, 0.5%, so 0. Yeah, that's correct. All right, calculator. Let's go to inverse normal. Inverse normal. Inverse normal. Okay, turn on the calculator. We go to second verse. Inverse normal. Area, this time we're gonna enter 0.005. Mu is 0, sigma is 1, and paste. I got this critical Z score equals 2.575829,303. We can round it up to 2.58. Let's do that. Okay, yeah, 2.58 already sounds good. Okay, so let's plug in. Sigma value, critical value is 2.58. And the sigma, recommended sigma, 19. Margin of error, 5. And then raised to power 2. Yeah, this is what I do in the calculator technology. I multiply, actually I already have the sigma, I already have the Z score, critical Z score in the calculator. I don't have to round it, you know. I already have 2.5758 blah blah there. And then I'm gonna multiply that, continue multiply that by 19. And then now I have 48.94-ish. And then divided by 5. Hold on. Let me clear that. And then divided by 5. I have 9.788 blah blah ish, right? And then I raise that to the power 2. I have 95.8079068. I have a decimal on the calculator, technology. 95.8079068. Well, sample size has to be a whole number, and we always have to round it up. So 96. Do you have the same thing, guys? Do you have a 96? Yes. Okay, very good. Perfect. Okay, since we use the whole population, 97, but hopefully close enough. Okay. You should have 95.8079. I think it would have to be 96, not 97. Oh, yeah. Thank you. Yeah, 97. Oh, okay, perfect. Yeah, Kelly got a 97, exactly. Oh, no, hold on. You got a 97? How do you get a 97? I got a 96. Did you round it? Let me try if I rounded the 2.58. 2.58 times 19 divided by 5 and then raised to our power 2. Oh, yeah, it's a rounding. You know what? I think we should put this value. Yeah, I misled you. My bad. Yeah, we should put that value for the critical value. And also another reason, because it's already there on the calculator. We're gonna do 2.575829,303. Make it as precise as possible. Yeah, my bad. I apologize. We don't round it. We should not round it. We should keep it as precise as possible. And we could, because when we use the function to get a critical value, and the critical value is right on the calculator, right? You just need to continue from there by multiplying 19, right? And then divide by 5. and then raise the answer to the power of 2. Yeah. I would say we would have to do that. Otherwise, the system might mark that wrong. Yeah. All right, Kelly. I apologize earlier. We should not round the critical value. We should not. We should keep the critical value as precise as possible. When we get a value from the calculator, it has many, many digits after the decimal point, right? Yeah, we should keep that way. Yeah, my bad. Yeah, we should do that. Then you should have 96. Yeah, also, there's no reason to round it. It's already there in the calculator, right? We just need to continue from there. Okay, so that we would have to stop here. We did cover all the 3 things we plan to cover. Even we did time to practice enough, but we did cover what we need to cover. We covered how do we use the technology to construct the confidence interval for population mean, right? Yeah, we introduced why we need to use t distribution instead of z distribution. And also we covered how do we use this formula. Why do we need to use this formula? And how do we use this formula to determine the sample size that just enough to construct the confidence interval with the predetermined confidence level and the margin of error. Next class to cover a couple of questions in this section before we move to the new chapter. That's it for today. If you have any questions, please feel free to email me. I'll say good night now. Yeah, let me take a picture of the because we have more students than the beginning of the class. The beginning of the class, I remember, has 11 participate. We have 1 more now. All right, we're done today. Have a good night, everybody. See you on Thursday.